Hello student. In today's session, we have to start new chapter from physics of 12th standard, section 2, and it's a chapter number 11, magnetic material. Now this chapter, magnetic material, we divided into two parts. The first part is related to the magnetic dipole and its moment. And second part is about the magnetic material. Now let me start with the topic number 1, magnetic dipole. So we already know that dipole, di means two, pole means, so here you magnet having a two poles, S pole, N pole. So it is a dipole. So two equal and unlike magnetic poles separated by finite distance constitutes a magnetic dipole. So you can see a magnetic dipole in a diagram. So this is S pole, this is N pole. So both poles are separated by some finite distance. So you can see here these are the two poles. This is S, this is N pole, and they are separated with some distance, and that distance is called as magnetic length. Second one is the geometrical length. So end to end length of the magnet is the geometrical length, and a line passing through both the pole is a magnetic axis. You can see this is a magnetic axis. And dipole moment, this is the direction of the dipole moment away from N pole and towards S pole. Now after that, finite distance of separation, it is a magnetic length that we already learned. Relation between magnetic length and geometric length. So magnetic length is 5 by 6 of geometric length. In a picture also you can see magnetic length means the distance between two poles of the magnet. And the poles are not at the end, it is just inside the edge of the magnet. So here magnetic length is smaller than the geometrical length. So what is the relation? The relation you can see here is the relation between this magnetic length and geometric length. Then after that, magnetic dipole moment. So magnetic dipole moment we are representing by capital M. So you can see a formula. So capital M into 2L. Capital M is the pole strength, 2L is the magnetic length. So multiplication of these two is called as magnetic dipole moment. So product of, so here product of pole strength and magnetic length. You can see here product of pole strength and magnetic length. It is called as magnetic dipole moment. So it is also called as 2ml. Magnetic dipole moment of bar magnet is given by this formula. Now magnetic dipole moment is a vector quantity and it is directed along the axis from fictitious south to fictitious north pole, south pole to north pole. So SI unit of magnetic dipole moment is ampere meter square. How we get this unit? You remember one thing here. For coil, magnetic dipole moment is given by formula. So current carrying coil is acting like a dipole, and dipole moment, magnetic dipole moment of the current carrying coil is given by formula NIA. So N is the number of turns, I is the current, A is the area. So SI unit we can write number a small n don't have unit. Capital I is the current. Current unit is ampere and area unit is meter square. So ampere meter square is the unit for magnetic dipole moment. So similarly, we can define a pole strength by using the same formula. So same formula we can use capital M is 2mn. So small m is equal to capital M upon 2n. So by using that also you can define a pole strength. You can see here. So capital M is the dipole moment, magnetic dipole moment, and 2L is the magnetic length. The ratio of these two is the pole strength. Now, the ability of magnetic pole to produce magnetic interaction, which is also called as pole strength. Now, SI unit you can write here. So unit for M is ampere meter square divided by the magnetic length is meter. So meter get cancelled and we get a unit ampere meter. So ampere meter is the SI unit for pole strength. Now next article is torque acting on a dipole in magnetic field. Now we consider a magnetic dipole of dipole moment capital M is placed in external magnetic field B as shown below. So you can see here. So this is a dipole. which is placed in magnetic field whose magnetic induction is B. Now here we have to discuss forces acting on this pole. So by using analogy between electric and magnetic field, we can write here magnetic induction is F by M. F is the force, M is the pole strength. So force is MB. So force acting on pole is given by formula MB. Now N pole having a pole strength plus M. So force acting on N pole, it is plus MB. And force acting on S pole. For S pole, pole strength is minus M. So force is minus MB. So here I can show both the forces in a diagram. So plus MB means I'm showing in the direction of magnetic field, and minus MB means I can show in the opposite direction to the B. So you can see here force acting on N. So this is direction of the force in the direction of B. So plus MB. So force acting on S, I can show it opposite to the direction of magnetic field. So it is, you can say that direction is opposite, so minus MB. So this is force. So both the forces are equal but opposite in direction. So here torque is there and we have to find out this torque. Now here this magnetic axis making angle theta with the direction of magnetic field, you can see theta, and this 2L is magnetic. Now here torque, you know the formula of the torque. Torque is given by formula 1 force into the perpendicular distance between the two forces. Now one force means we can use this MB is the one force, and perpendicular distance between the two forces, this NP is the perpendicular distance here. You can see this line NP. So this is a perpendicular distance between two forces. So here torque is equal to MB into this NP. Now this NP is opposite side of this theta. So by using this triangle, I can find out NP. So this is theta. So theta NP is opposite side of the theta. So I can use a sine theta. Sine theta is NP by 2L. Sine theta we can write NP by 2L. So NP is 2L sine theta. So that we have to substitute. So you can see in the next step. So this is our formula. Now sine theta is NP by 2L. So NP is 2L sine theta. Let me substitute and then equation of the torque become. So torque is equal to this MB into this 2L sine theta. Now this formula we can write 2. I write first, then M, then L, then this B, and then sine theta after rearranging the term. And this, you know that this 2ml, this is capital M. So instead of this 2ml, I can write capital M. So we get this formula torque is equal to MB sine theta. And this is the final formula of the torque acting on dipole. In vector form, the same formula we can write torque is equal to M bar cross B. So M bar cross B bar we can expand and we get a magnitude like this. So just we get here the formula of a torque. Now let me learn the cases also. Case 1, if theta is 0, means if this angle theta is 0, it means that this magnet, means the axis of the magnet is parallel to the direction of magnetic field. Then theta is 0. Then sine 0 is 0. We are using this formula. Sine 0 is 0. So if sine 0 is 0, 0 multiplied by MB is 0. So torque acting on a dipole is 0. No torque when axis of the magnet is parallel to the direction of magnetic field. Now second case, theta is equal to 90, means if the magnet axis is perpendicular to the direction of magnetic field, then sine 90 is 1, and if sine 90 is 1, then we get torque is equal to MB, and a maximum torque is acting on this dipole. Then after that, next article is potential energy of a dipole in external magnetic field. Torque acting on magnetic dipole in external magnetic field is given by, just we derived a formula of torque that we are written. Now, work done by a torque to rotate dipole from this angle theta 0 to theta. Now we have to rotate a dipole with this angle. Then work done is given by this formula. Work done is equal to integration of this torque, external torque multiplied by this d theta. So you know that work done, we are rotating here. So work done is torque into this displacement. Now here, torque, external torque into d theta. Now external torque is given by this formula. Let me substitute here mb sin theta and this d theta as it is. Now let me take constant outside. This m and b is a constant, both. Then theta 0 to theta, this sin theta d theta. The integration of sin theta d theta is minus cos theta. So here I written minus cos. Then within the limit theta 0 to theta. Then after that we have to substitute limit here. So let me substitute upper limit first instead of theta. So it is theta. So minus cos theta, then minus sin, and then lower limit we have to substitute. Minus this minus of cos theta. Then after that this minus minus is plus. So here then I can write this cos theta 0 first and the cos minus cos theta later. So we get work done is equal to this. So this mb cos theta 0 minus cos theta. Then after that, in the next step, initially let axis of the dipole be perpendicular to the field. Then we can write theta 0 is 9 and this cos 90 is coming 0. So because of that we get work done is equal to minus mb into this cos theta. So listen, if we substitute theta 0 is 90 in the previous formula, then we get this. Now after that, potential energy is equal to the work done. So we already have a work done formula. Now we can write potential energy is equal to that. Potential energy is equal to minus mb cos theta. Or we can write m bar minus sign as it is m bar dot b bar. So this m bar dot b bar we can again expand like this. So here we get a formula of potential energy. Now let me learn the special cases. Now case number 1. Theta is equal to theta 0. Sorry, theta is equal to 0 degree. If theta is equal to 0 degree, then you know that cos 0 is 1. If cos 0 is 1, then potential energy is minus 1. Second case, theta is 90, then cos 90 is 0, then potential energy is coming 0. And the third case, theta is 180 degree, then cos 180 is minus 1. So here minus minus plus, so potential energy is plus mb. So these are some special cases of the potential energy. Note that potential energy of the dipole is minimum when theta is 0. You can see here theta 0, then it is minus. And hence it is in stable equilibrium. And it is stable only when this potential energy is minimum. Now after that, the next article, vibration of magnet in external magnetic field. And the example is vibration, this is magnetometer, vibration magnetometer. Now we consider here a freely suspended bar magnet when displaced through a small angle theta from equilibrium position in external magnetic field, and then it experiences torque. How much is the formula of the torque? Minus mb sin theta is the torque. Okay. So this is the torque. And the torque we can write I alpha. Now I is a moment of inertia. Alpha we can write d square theta by dt square. So you know that alpha is d omega by dt, and then d by dt as it is, this omega is d theta by dt. So we get d square theta by dt square. This is alpha, so that we substitute. So we get this formula. I d square theta by dt square is equal to minus mb sin theta. For small angle sin theta nearly equal to theta, so we can use I d square theta by dt square is equal to minus mb into this theta. Now I we can shift to this right hand side. So we get d square theta by dt square is equal to minus mb divided by I into theta. So this is the formula and this is equation number 1. So here d square theta by dt square is alpha that you remember. Now here after that this motion of magnet is angular system. We learn in chapter 4 oscillation, in chapter 5 oscillation. So if this is a condition for angular resistance, or we can write this angular acceleration directly proportional to this angular displacement and both are oppositely directed, then it is angular SHM. So here the motion of magnet is angular SHM. Then I write the same formula again. Then after that we know the equation of linear SHM. Linear SHM, this is a differential equation of linear SHM. D square x by dt square is equal to minus omega square x. So you can see, so this is as equation 1 and this is equation 2. By using this equation 1 and so we can write this omega square is equal. So omega square is equal to this mb divided by I, or we can write omega is equal under root mb by I. So we can write the period of vibration here. Period is 2 pi by omega, and this omega we have to substitute in this formula of period. Then we get a formula for period of vibration. Now we start a next article. Magnetic dipole moment of revolving electron. In the previous standard, we already learned a current carrying conductor acts as a magnetic dipole. Similar manner here. If it is a revolving electron, so revolving electron is equivalent to the current carrying conductor. Means inside the current carrying conductor, electrons are revolving. Similar manner here, inside the atom also, electrons are revolving around the nucleus. So revolving electron and this current carrying circular loop both are equivalent. Then let me find out magnetic dipole moment of revolving electron. So we consider here electron is revolving around the nucleus. Now here we consider some factors. So first one is this capital small r is the radius. Then v is linear speed of the electron. As the electron revolving in a circular way, so this I is a circulating current. Then this capital M is the magnetic dipole moment of this revolving electron. So this capital L is the angular momentum of this revolving electron. And this E is the charge. So the electron having a negative charge. So E minus 1 also we can write, or simply E we can write a charge on electron. Now we have to write a magnetic dipole moment of revolving electron. Let I tell you a basic procedure. Magnetic dipole moment for a coil is NIA. Now here it's a revolving electron. So number of turns is not coming here. I into A. I is the current, A is the area. So circulating current we find out first, and then area we know that pi r square. By substituting this, we get magnetic dipole moment of the revolving electron. Now how we find out this circulating current first? So we write here first period of revolution of this revolving electron. So in circular motion article, we already learned this is the period of revolution formula 2 pi r by v. Then we can write as equivalent current or circulating current produced by this revolving electron is current is charge by time. So charge on electron is E and time is a capital T we can use. So this capital T we substitute here, we get current. So after substitution, we get this current is EV divided by 2 pi R. This is a current. Now we have to substitute this current in a formula of magnetic dipole moment. Hence, magnetic dipole moment is I into A. So I is EV divided by 2 pi R and this A area is pi R square. So this is a magnetic dipole moment. Then after that, this pi and this pi get cancelled. This R get cancelled. So we get a formula EVR by 2. And this is a final expression for magnetic dipole moment of revolving electron. In previous board exam also question is also asked obtain expression for magnetic dipole moment of revolving electron. Then you have to write up to this. Now let me modify this. So this dipole moment is directed along axis in the sense given by right hand. Now from equation number 2, I can write a term by rearranging term. You can see here EVR by 2. I can multiply it by m and divide by m. So m is the mass of electrons. And then we get this term. E into this mvr divided by 2m. After doing the multiplying by m and dividing by m. And this mvr or mrv, it is the angular momentum. So angular momentum is represented by L. So, but here L is equal to mvr. Hence, this dipole moment we can write EL by 2m. Then after that, so here L is the angular momentum of the revolving electron. So same formula we can write in vector form also. Then negative sign indicate that angular momentum and this dipole moment, they are directed opposite to each other. So negative sign is there. Now after that, we can transfer this angular momentum to this side. Means in magnitude wise, I can write the formula. Magnitude I am writing, or by using this I write m by L is equal to E by 2m. And this m by L is called as gyromagnetic ratio. And so gyromagnetic ratio formula is E upon 2m. So let's see a more detail about the gyromagnetic ratio. What is gyromagnetic ratio? So next article is gyromagnetic ratio. Now gyromagnetic ratio is the ratio of m and L. M is the dipole moment, magnetic dipole moment, and L is the angular moment. The ratio of magnetic dipole moment to the angular momentum of revolving electron is called as gyromagnetic ratio. And it is given by formula E upon 2m. So this is the gyromagnetic ratio. Question is already asked in the board exam, define gyromagnetic ratio, or what is gyromagnetic ratio, that you have to write up to this. Then after that, by Bohr's theory, let me modify this formula. By Bohr's theory, angular momentum is given by mrv, and it is equal to nh upon 2 pi. You already learned this formula in the 10th standard as well as 11th standard also. So this is the angular momentum by Bohr's theory. Now, magnetic moment of electron m is by using this formula. So we can write this m is equal to EL by 2m. Then, so this is magnetic dipole moment. So this L we can write by using this. Then we get E by 2m as it is, and this is L. L is nh upon 2 pi. After writing it in a proper way, we get E and h divided by 4 pi. So this is the formula for capital M. The term EH, this term EH divided by 4 pi m, it is also called as Bohr's magneton. Now, next article is magnetization and magnetic intensity. Magnetization. So it is a magnetic dipole moment developed per unit volume. It is a magnetization. It is also the pole strength developed per unit cross-sectional area. Now we get this formula. Now see here, this is a magnetization. Magnetic dipole moment divided by volume. And dipole moment, you know that pole strength into this magnetic length. And this volume of a bar magnet, we can write this cross-sectional area. I can write it by small a, and 2L is its length. So 2L. So this 2L get cancelled. So we get a formula m by a. So this m, small m is a pole strength, a is a cross-sectional area. So multiplication of these two is, sorry, division of these two is also magnetization. In examination, a question is already asked, define magnetization. You can write by this or by using this. Magnetization, magnetic dipole moment per unit volume is a magnetization. So unit you can write here, capital M having a unit ampere meter square divided by volume meter cube. So this meter square and meter square from this meter cube get cancelled. So we get ampere per meter is the SI unit. Now let's see here. Next is a magnetic intensity. Magnetic intensity represents the strength of magnetic field. So it is represented by H. H is equal to B by mu. Or we can write now magnetic susceptibility. It is the ratio of intensity of magnetization of material to the magnetic intensity of the field. So mz divided by h, magnetization, and this is magnetic intensity. Now next definition is magnetic permeability. It is the ratio of magnetic induction of material to the magnetic intensity of the field. You can see a formula, magnetic permeability. Relative permeability. So the ratio of magnetic permeability of medium to the permeability of free space is called as relative permeability of medium. It is represented by mu subscript r. You can see this mu r is equal to mu by mu g. So this is permeability of medium to the permeability of free space. Then after that, relation between magnetic permeability and susceptibility we have to learn. Magnetic flux density inside toroidal solenoid carrying current I is given by. So this is a magnetic field inside toroid, mu 0 n I. So this n is the number of turns per unit length. Or we can write n into I as a h also we can write. So n is the number of turns per unit length, h is the magnetic intensity. Now if we consider, so this is a toroid and inside the toroid iron core is present. This is in absent of iron core, this is a magnetic field due to this toroid. But inside this iron core is present, then this iron core also contributes some magnetic field. And then magnetic field due to this uh, the toroid which is with iron core is given by formula this B0, this magnetic field plus Bm. B0 is Bm is the magnetic field contributed by this iron core. And it is given by formula mu 0 into this mz. Mz is the magnetization. So let me substitute B0 by this formula here and Bm by this. Then we get a next formula. B is equal to B0 plus Bm. Then I substitute here B0 and Bn. Then we get this formula. Then mu 0 we can take common. Then we get H plus Mz. Then this magnetization we can write susceptibility into this magnetic intensity H by using this formula. Then we get this equation for B. Then here H we can take common. Then mu 0 H is outside and then 1 plus susceptibility is in a bracket. Now this 1 plus susceptibility is a relative permeability. So before I can write it here. B is written here mu H. Okay, mu H is written and then this mu 0 H as it is. This 1 plus susceptibility is also as it is. Now 1 plus susceptibility we can write relative permeability. Let me write it in the next step. Or before that, okay, here some alternate steps are written. This H get cancelled. Mu divided by mu 0 is 1 plus susceptibility. This formula we get. And this is equal to the relative permeability 1 plus susceptibility. So we get a formula mu r is equal to mu upon mu 0. Hence, we can write mu by mu 0 is equal to mu r. So you have to remember these formulas for solving problems. Now we start classification of magnetic material. Classification of magnetic material. So based on behavior of material in an external magnetic field, the materials are classified under three categories. The first one is diamagnetic substances. Now what is diamagnetic substances? These are the substances which are weakly repelled by magnetic field because they get weakly magnetized in the direction opposite to the field. So when these diamagnetic substances are placed in magnetic field, they are repelled. Based on the magnetic properties, we are classifying the material into three categories. Means if we place a substance in magnetic field and they are weakly repelled, then they are coming under diamagnetic substances. The examples of diamagnetic substances are copper, bismuth, antimony, mercury, water, air, hydrogen, etc. Many examples we can give. Now after that, the second one is paramagnetic substances. Basically, these substances are weakly attracted by magnetic field because they get weakly magnetized in the direction of the field. So here, the examples of the paramagnetic substances are aluminum, magnesium, chromium, platinum, oxygen, etc. When these substances are in magnetic field, they are weakly attracted by the magnetic field. So they are coming under the paramagnetic substances. And the last one is of ferromagnetic substances. So these are the substances which are strongly attracted by magnetic field because they get strongly magnetized in the direction of field. Hence here we classify the substances into three categories: di, para, ferro. Di means weakly repelled, para means weakly attracted, ferro means strongly attracted. The example for ferromagnetic substances are iron, nickel, cobalt, alnico, and steel, etc. These are the examples of ferromagnetic substances. Now let's see some properties of these substances. Let me start with the diamagnetic substance. Properties of diamagnetic substances. Basically, the first property we have to see. The first property is when they are placed, when they means diamagnetic substances, placed in uniform magnetic field, they move from a region of stronger field to region of weaker field. They move from stronger to weaker part of the field. This is basically because when we place diamagnetic substances in magnetic field, if this is a strong magnetic field, I consider here it is a strong magnetic field and this is weak magnetic field. We are placing this in non-uniform magnetic field. Non-uniform means it is not constant. If we place diamagnetic substance here in between these two, then they are means diamagnetic substance is repelled by both the fields. So strong magnetic field repelled it very strongly, so it moves from stronger part of the field to the weaker part of the field. Now, the second property is when they are placed in external magnetic field, they get weakly magnetized in the direction opposite to the field. So when diamagnetic substances are placed in magnetic field, they are weakly magnetized in the direction opposite to the direction of field. Third one, a diamagnetic liquid taken in a watch glass is kept between two dissimilar poles pieces of magnet. A small depression is created in the middle. So we are talking about a watch glass, this shape watch glass. So it is filled with diamagnetic liquid. And when such watch glass is placed on two dissimilar poles, this is N pole and this is S pole, then this liquid is repelled, weakly repelled by the magnetic field, and magnetic field is strong between these two poles. So in the central part here, or whatever the liquid present, it is repelled. So it is repelled more. So in the center, we get depression. So depression in the middle is also. So similar manner, same properties we can write for para. You know that di is weakly repelled and para is weakly attracted. So these behavior is opposite. For paramagnetic, opposite behavior we observe. So here in depression we observe in diamagnetic. So in para we can get elevation. So in the previous property, it moves from stronger to weaker field. Then para move from weaker to stronger. So that also we have to learn it later, but comparative study make it more easier that you remember the same type of properties we are learning, but separately we are learning. Okay, so I hope you understood this one. Now after that, next one, a rod made up of diamagnetic substance when freely suspended. So when diamagnetic rod is freely suspended in uniform magnetic field, then it come to rest with its length perpendicular to the direction of field. So you can see it in a picture. So here diamagnetic rod is perpendicular. Why it is perpendicular? The reason is this rod is repelled by both the poles. So it tries to acquire a minimum area. So that's why the rod is perpendicular to the direction of magnetic field. Then when we are talking about paramagnetic, then it is attracted by both the poles. Then that time maybe instead of perpendicular, the rod is parallel to the direction of magnetic field. So that we learn in the next one. But here in case of diamagnetic, rod is coming to rest with its length perpendicular to the magnetic field. You can see this is the direction of the magnetic field and this is a rod. They are perpendicular. Now next one is a diamagnetic liquid is taken in U-tube. So U-tube means U-shaped tube. You can see in a picture. So this is a U-shaped tube. So inside that a diamagnetic liquid is there. And one arm of that U-shaped tube is placed in magnetic field. Then the liquid in that arm is repelled by the magnetic field. So as the liquid repelled, it means that here depression or a decrease in the level we observe. So you can see here, the liquid in that arm falls. Falls means the level decreases. Now next one, a diamagnetic gas when introduced in a magnetic field, it spread perpendicular to the direction of field. Similar manner, this is N pole, this is S pole. When we spray diamagnetic gas, so it spray perpendicular to the direction of magnetic field. It is similar to the rod. Rod is also coming to the rest with its length perpendicular to the magnetic field. Now next one is magnetic moment of each atom of diamagnetic substance is. So here, when we are talking about magnetic dipole moment, so this is a diamagnetic substance. Then here, the dipole moment of this atom is in this direction. The next atom is in opposite direction. So if we consider one atom having a dipole moment in this direction, so another atom may have in this direction. So dipole moment, this cancel with this cancel with this. So resultant dipole moment of diamagnetic substance is 0. So magnetic permeability of diamagnetic substance is slightly less than 1. So magnetic permeability we represent by mu. So it is less than 1. So remember this value. This is magnetic permeability means what that we already learned in the previous lecture. So here you remember it is less than 1, slightly less than 1 for diamagnetic substance. Maybe in MCQ question is asked if permeability of the substance is 0.81, then the substance is. You remember if it is slightly less than 1, then it is a diamagnetic substance. Magnetic susceptibility now. So susceptibility is a small and it is negative. Susceptibility is small and negative and is independent of temperature. You can write the separate property also. Magnetic susceptibility of diamagnetic substance is independent of temperature. Susceptibility and temperature, no relation. But for para, it has a relation that we have to learn later. So you remember here, Permeability, magnetic permeability slightly less than 1. Susceptibility small and negative. If someone asks in examination or in MCQ, susceptibility of the material is minus of something, then you have to remember if susceptibility is negative, then it is a diamagnetic substance. Now, origin of the diamagnetism. So basically, in diamagnetic substances, dipole moment of so dipole moment of all electrons of atom cancel each other. We already discussed. So when this is dipole, this is diamagnetic substance, dipole moment of one atom in this side and another atom in this side. So they cancel with each other. As a result, zero dipole moment for diamagnetic substance. When a diamagnetic substance is placed in external magnetic field, the magnetic flux associated with each electron orbit changes. Therefore, a current is induced in a substance. The induced current accelerates some electrons orbiting in one direction and retard those orbiting in opposite direction. As a result, substance acquire an induced magnetic moment in the direction opposite to the applied. So substance acquire a magnetic moment which is opposite to the direction of applied field, and because of that, the substance is repelled by magnetic field. So substance acquire magnetic moment, but this magnetic moment, acquired magnetic moment, is opposite to the magnetic field, and therefore when we place such substance in magnetic field, it is repelled. Now after that, next we have to talk about the properties of paramagnetic substances. Now diamagnetic and paramagnetic substances having a similar type of the similar means slightly different properties. Means in di it is perpendicular, here it is parallel. So that let's see. So first property, when paramagnetic substances are placed in non-uniform magnetic, then they move from weaker to stronger field. In para, it is stronger to weaker, here weaker to strong. So that you remember. Now next property. When they are placed in external magnetic field, when they are placed in external magnetic field, they get weakly magnetized in the direction of field. So in para, in the direction of field, but in di we learn opposite to the direction of field. Now next, a rod made up of paramagnetic substance, when freely suspended in uniform magnetic field, it comes to rest with its length parallel to the direction of magnetic field. So in the die, it is perpendicular to the direction of magnetic field. Here it is parallel to the direction of magnetic field. Next one, a paramagnetic liquid is taken in a watch glass, is kept between two dissimilar poles of magnet. Small elevation is created. Here elevation. So you can see here. So when a watch glass containing this paramagnetic liquid is placed, so magnetic field is more between the two poles. So it is attracted more and more liquid is attracted in the center. So here we get a small elevation. So in that die we get depletion, but here we get elevation in the middle. Now next one. A paramagnetic liquid is taken in a U-tube with one of its arm held between two dissimilar pole pieces of magnet. Level in that arm rises. The similar property within the die also. So liquid level decreases in die, but here when this U-shaped tube containing this paramagnetic liquid and one arm is kept between the two poles, then level of liquid in that arm increases. Why increases? Because liquid attracted due to this magnetic field, and liquid rises here. The next one, a paramagnetic gas when introduced. When we are talking about gas, it is similar to the rock. Introduced in magnetic field, then gas spread parallel to the direction of field. Magnetic moment of each atom, next property, magnetic moment of each atom of paramagnetic substance is slightly greater than 0. So magnetic moment we are talking. So it is slightly greater than 0. So in di it is 0, but it is slightly greater than 0 in para. Magnetic permeability, slightly greater than 1. In di it is slightly less than 1. Here it is slightly greater than 1. You remember it. So if magnetic permeability is 1.2, then the substance is paramagnetic, slightly greater than 1. Magnetic susceptibility, small and positive. In case of di, it is small and negative, but here it is positive. And is inversely proportional to absolute temperature. Means susceptibility inversely proportional to absolute temperature. So remember this relation for solving the problems also. Susceptibility and temperature, they have an inverse relation. Now, origin of paramagnetism. So in paramagnetic substances, the magnetic dipole moment of all the electrons of an atom do not cancel each other. Here dipole moment is slightly greater than 1. So they are not cancelling with each other. As a result, an atom of paramagnetic substance has small magnetic dipole moment associated with it. Thus, behaves like a tiny magnet. And that or it is called as atomic magnet. In absence of magnetic field, the axes of all the atomic magnet are oriented randomly. Hence, resultant magnetic moment of the substance is 0. When paramagnetic substance is placed in external magnetic field, the axis of all the atomic magnet get aligned in the direction of applied. The substance acquire a resultant magnetic dipole moment in the direction of applied field and is attracted by the field, and therefore it is attracted by the field. As soon as the field is removed, means if you remove the magnetic field, the axis of all the atomic magnet are oriented randomly again. So you can see in a picture. So initially they are randomly arranged, and then in external magnetic field they align in the direction of magnetic field. Again, as we remove the field, again they come to the original position. Then next article is Curie law. So according to Curie, the magnetization of a paramagnetic substance is directly proportional to magnetic field, external magnetic field. Magnetization directly proportional to external magnetic field, and inversely proportional to absolute temperature. Means temperature in Kelvin. So you can see here, when we combine these two equations, we get this one. And if we place a constant here by removing the proportionality sign, then C is a constant and it is called as Curie constant. If you remember this formula, you can able to write the Curie law. So you know that B is equal to mu 0 H, and if we substitute B here, we get magnetization is equal to C into mu 0 H divided by T. So we can transfer this H to this side, we get this formula. This is formula is only. But here, this susceptibility is this mz divided by H. Magnetization divided by magnetic intensity is susceptibility. The susceptibility we can write. Susceptibility is equal to C mu 0 by T, or susceptibility inversely proportional to T we can write. C is a constant, mu 0 is a constant. So susceptibility inversely proportional to this T. And this law is for a paramagnetic substance, because diamagnetic substance and susceptibility don't have any relation. So in the properties of the para also we learn paramagnetic susceptibility inversely proportional to absolute temperature, and that we proved here. So you can see it here. Now we start properties of ferromagnetic substance. So here, ferromagnetic substances mean the substances which are strongly attracted by magnetic field. And what about para? Para means weakly attracted. So here you remember one thing here. So para, ferro both are attracted by the magnetic field. But para is weakly and here ferro is strongly attracted. So here ferromagnetic shows all the properties of paramagnetic substances, but in greater extent. So let's see some properties. See the first one. Ferromagnetic substances possess all the properties of paramagnetic substance, but in greater extent. Ferromagnetic substances are used to make permanent magnets. So you can see a permanent magnets in a laboratory, the bar magnets. That bar magnets are made from the ferromagnetic substances. When ferromagnetic substances are heated above the Curie temperature, they lose their ferromagnetic properties and converted into paramagnetic. So you can remember one thing here. What is Curie temperature? Also, in another way, you can write the temperature at which ferromagnetic substance converted into paramagnetic substance. That temperature is the Curie temperature. Next one, magnetic moment of each atom. So here this property is about magnetic moment of each atom in ferromagnetic substance is much greater than 0. So it is greater than 0. Magnetic permeability. So magnetic permeability, here this is about magnetic permeability. It is greater than 1, much greater than 1. You can remember this one. So I told you it shows the properties of para, but in greater extent. For para, it is greater than 1. It is much greater than 1. Magnetic susceptibility now. So in para, susceptibility is small and positive. So here it is susceptibility large and positive. And it is inversely proportional to temperature. Susceptibility and temperature relation is inverse relation, which is similar to the para. Now next one is origin of ferromagnetism. And that origin of the ferromagnetism we are explaining by using domain theory. So basically, what is domain theory? So what is domain first? So according to the domain theory, a ferromagnetic substance is divided into large number of small regions. All the regions are called as domain. So you can see here a diagram. So in that diagram, we shown a 4 domain. And this is ferromagnetic substance. We can classify it into some smaller regions. So every part is called as domain. Domain means inside that. So domain means a small region of ferromagnetic substance that you remember here. Now let's see more about this. The axis of all the atomic magnet in one domain are aligned in the same direction. You can see here. So all atomic magnet having their dipole axis means axis of this dipole moment in the same direction. In absence of magnetic field, the axis of all the magnetic domain are oriented randomly. Hence, resultant magnetic moment is 0. You can see here. So this and this, they cancel with each other. So this one and this one, so they cancel with each other. So resultant magnetic moment is 0 in absence of magnetic field. Now you can see this is a picture in absence of magnetic field. Now you can see a picture B. So in presence of magnetic field. So this is weak magnetic field. So let's see. So when ferromagnetic substance is placed in weak magnetic, first is weak magnetic field. So you can see a direction of the magnetic field here. So this is the direction upward. Then individual atomic magnet tend to align their axis parallel to the direction of magnetic field. So you can see here. So this align in the direction of magnetic field. So other also mean maximum atomic magnet align their dipole moment in the direction of magnetic field. As this is a weak magnetic field, so maximum, majority, they align in the direction of weak magnetic field. As a result, there is a shift in the domain boundary. So some domain boundaries are shifted. You can see here. So this is larger domain now. So shifting of the domain boundaries are there. And substance gets some magnetic dipole, net magnetic dipole. Now here the net magnetic dipole is not G. So substance having some a dipole moment. As soon as the field is removed, now as we remove the magnetic field, domain boundaries return to their original position. Means we get a similar picture again. So we get this type of picture when we remove the magnetic field, and substance loses magnetism. Substance loses magnetism. Okay. Now again, now when we place it in strong magnetic field, so when magnetic field is very strong, then all the domain align their dipole moment very abruptly in the direction of magnetic field. You can see here in the third diagram. So this is magnetic field. So all the domain now you can see in the direction of magnetic field. So they align very abruptly. So here the substance gets strongly magnetized, and it is magnetized in the direction of applied field. And because of that, when a ferromagnetic substance, and because of that, you remember here, when it align their dipole moment very abruptly in the direction of magnetic field, domain structure here get destroyed. As we remove the magnetic field here, then also domain boundaries does not return to their original position. Means substance retain magnetism when it is placed in strong magnetic field. Substance retain magnetism. So, and by using this, we can make a permanent magnet also. You know that in a laboratory, whatever the magnet, bar magnet, you can see it is iron piece. It is strongly magnetized. It is very strongly magnetized so that it retain the magnetic properties as we remove the magnetic field, and then it become a permanent magnet. So effect of temperature on ferromagnetic. When ferromagnetic substance is heated, due to increase in thermal vibration, the coupling between atomic magnet becomes loose. Finally, a particular temperature, at particular temperature, this coupling break and the axis of all the atomic magnet in the domain get oriented random. The domain structure get destroyed and ferromagnetic substance get converted into para. Means what is the effect of temperature? You remember. Ferromagnetic substance converted into paramagnetic substance. And here domain structure destroyed. As it is not become a ferromagnetic, so domain structure is no longer exists. The temperature, you remember here a definition of the Curie temperature. The temperature at which domain structure of ferromagnetic substance break and it is converted into paramagnetic substance, it is called as Curie temperature. In previous examination question is asked what is Curie temperature, so you can remember. So domain structure break and so ferromagnetic substance converted into paramagnetic. That temperature is called as Curie temperature. Magnetic susceptibility of ferromagnetic substances varies with temperature, as you can see a relation between susceptibility and temperature of ferromagnetic substance. So you know that susceptibility inversely proportional to the temperature. So the relation now, this is a relation. And graphically you can see. So here, so this is Curie temperature. So as we increase the temperature, then susceptibility decreases, and at one particular susceptibility or at one particular temperature, it is converted into the para, and that temperature we called it as a Curie temperature. Now here it is a paramagnetic substance. From magnetic material, So question number 1 we have to start, and it is MCQ. The intensity of magnetic field of the earth at a point inside hollow iron box. So magnetic field intensity inside hollow iron box. So we already have idea about the properties of magnetic lines of force. Magnetic lines of force pass through insulator but does not pass through conductor. So this iron box is a conductor. So no magnetic lines of force inside the iron box. So therefore we can say that there is no intensity, means intensity of magnetic field inside this iron box is zero. Now question number 2. Soft iron is used to make the iron core of transformer because listen, we are using soft iron to make a core of the transformer. The reason for this is low coercivity and low retentivity. Next one. Which of the following statement is correct for diamagnet? We are talking about diamagnetic material. So for diamagnetic material, relative permeability is less than 1, it is right. Susceptibility is negative and low, this is also right. Susceptibility does not depend on the temperature, so this is also right. So all of the above, this is the correct option for this question. Next one. A rectangular magnet suspended freely has a period of oscillation T. So magnet having a period T. Now it is broken into two equal parts or two equal halves, each having half the original length. So length is half of that. One piece is made to oscillate freely. Period of oscillation is T dash. So period of oscillation of half piece means one piece is T dash. Then we have to write a ratio of these. So we have an idea about period. T is equal to 2 pi under root I upon mb. So this is the formula for period of oscillation of bar magnet. Now pay attention here. So here period depends on this moment of inertia. So moment of inertia depends on length. So it's a bar magnet. So moment of inertia of this is m L square by 12. So here this is the moment of inertia. Now here we can say that so it depends on moment of inertia as well as inversely depends on dipole moment also. So because when bar magnet is broken, dipole moment also changes. So remember one thing here. So in case 1, if I consider moment of inertia is m L square by 12. In second case, moment of inertia is basically case 2. Mass is half, so m by 2. So length is also half, so L by 2 square divided by 12. So this is the moment of inertia. So I can write m L square by 12 into this 8. So this is the moment of inertia. As well as so dipole moment. So this is about moment of inertia. Now similarly about dipole moment, case 1. So dipole moment capital M is equal, or we can use here mu also for dipole moment. So dipole moment I can write M in case 1. In case 2 I can write dipole moment in the case 2 is M by 2 because length is reduced to half. So this is dipole moment. Now here we have to substitute in a formula these things. So let's see what we get after substitution. Now So this T dash divided by T. So is equal to, so I upon M. So T dash, so I is M L square by 12 into 8 divided by, so second I is, so M L square by 12 multiplied by, so M, dipole moment is inversely proportional. So in case dipole moment of case 2, so dipole moment of case 1 divided by dipole moment of case 2. So it is M, and here it is M by 2. So that we have to use. Now let me cancel the things and we get the final answer. ML square get cancelled, well get cancelled, and get cancelled. So what we get here? So here we get, so root 1 by 8, and here we get 2 by 1. So in a root 1 by 4 we get, it means that 1 by 2. So 1 by 2 is the answer, and it is written in the option B. So option B is the right answer for this question. Now after that, next one. Magnetizing field of 360 ampere per meter produces magnetic flux density 0.6 Tesla in ferromagnetic material. What is permeability? So we have to find out permeability. See here, and also answer is displayed here. So here, magnetizing field means magnetizing field is given, magnetization basically. Magnetic flux density 0.6 and permeability is B by magnetizing field. So B is 0.6 and here magnetizing field is 360 ampere per meter. So by solving this, we get answer 1 by 600. So I think here some printing mistake is there. Here 0.6 divided by 360. So we can write here 6 by 360 into 10. So we can write here it is 1 by 6 by 3600 means 1 by 600. And this is the right answer. Now next question. The work done for rotating a magnet with magnetic dipole moment F through 90 degrees. We have to rotate dipole with 90 degrees. From its magnetic meridian is n times the work done rotating through it 60 degrees. Find the value of it. Now what they given? They given the relation between two work done. Now let's see the given here. So basically, so theta 0 is 0, initial angle is 0. Now we have to rotate it initially 90 degree and then we have to rotate with 60 degree. And then work done in both the cases, work done to rotate 90 degrees W1 and work done to rotate by 60 degrees W2. The relation between these two work they given n times. W1 is n times the W2. And we have to find out this n. Now we write down, we find out W1, we find out W2, and then we use this relation to find out this n. Or we can do one thing here. So this n is equal to W1 by W. So we find out W1, W2, and then we can use this one. Now you can see here, work done by external agent to rotate theta 0 to theta, means 0 degree to first 90 degree. So it is given by, this is a formula. In that formula, theta 0 is 0 and theta 1 is 90. So by substituting this, we get here theta 0 means cos 0 is 1 and cos 90 is 0. So this get cancelled. So we get MB. So this is the work done. Similar manner, we can find out work done to rotate from 0 to 60 also. So similarly, from 0 to 60 degree, we have to find out work done. So here MB into cos, same formula, only the thing is here theta is 60 degree and here the initial angle is 0, 0 to 60 we have to rotate. Now cos 0 1 and cos 60 is minus 1, means cos 60 is 1 by 2. So this minus sign as it is. So 1 minus 1 by 2 is 1 by 2. So 1 by 2 means 0.5. So we get this one. Now we can find out n is equal to W1 by W2. So W1 is MB and W2 is 0.5 MB. So MB get cancelled. 0.5. 1 upon 0.5 is 2. So n is equal to 2. So this is the final answer. Now next problem. Problem number 11. The susceptibility of paramagnetic material is X. Means it's the symbol we use. It is at 27 degrees Celsius. What temperature susceptibility is 1 by third of the previous one? Susceptibility divided by 3. Now here the given thing. So here the given susceptibility 1. So we can use susceptibility 1 is this one. Susceptibility 2 is divided by 3. Okay, temperature 127 degrees Celsius in Kelvin it is 300 and temperature 2 we have to find out. So we use the relation between susceptibility and temperature, and the relation is susceptibility inversely proportional to the temperature. So this is the relation. So we use the relation. So this is the relation here. Now here we can use now susceptibility 1 divided by susceptibility 2 is equal to temperature 2 by temperature 1 because the inverse relation. Now let me substitute the values. So after substitution of value and doing the calculation for T2, so we get here susceptibility 1 is this, susceptibility 2 is divided by 3 into T1 is 300. This get cancelled. 3 into 300, it is 900. So 900 Kelvin is the answer for this problem. So this is the temperature 2. My next question. When a plate of magnetic material size is 10 centimeter into 0.5 centimeter into 0.2 centimeter, length, breadth and thickness they given, is located in magnetizing field. So this is a magnetizing field, 0.5 into 10 raised to 4. Then magnetic moment of 5 ampere meter square is induced in it. Find magnetic induction in the rod. So we have to find out magnetic induction. So let's see length, breadth and height. Then they given here magnetizing field, intensity of magnetization. Then magnetic dipole moment they given here. And we have to find out magnetic induction, means B we have to find out. So first we find out the volume of the plate. Length, breadth, height is the volume. So after multiplying these three, length, breadth and height, we get 1 centimeter cube. 1 centimeter cube is the answer for volume. Now this we can write centimeter to meter 1 into 10 raised to minus 6 meter cube. So this is the volume. Then after that, magnetic induction or B is equal to mu 0 is H plus mz. This is the formula. And in that formula, we have to substitute H, M. These two we have to substitute. So this mu 0 as it is. Then magnetization is magnetic dipole moment upon volume. This magnetization is not given, but magnetic dipole moment is given and volume is not. So magnetic dipole moment per unit volume we use for that. Then after substitution, mu 0 is 4 into 10 raised to 7 minus 7. H is given here 0.5 into 10 raised to 4. And this magnetization, magnetic dipole moment is 5 and volume is 10 raised to minus 6. So we have to do this calculation to get the final answer. And after doing the calculation, we get final answer 6.290 Tesla is the magnetic induction.